Our topic is heterogeneous permeability and series and parallel flow in a hydrocarbon-bearing reservoir. This project pertains to petroleum 4050 reservoir dynamics. Our names are David Troche, Zach Pishota, Austin Slavins, and Ben Cartner. Heterogeneity is an important aspect of fluid flow in hydrocarbon reservoirs, so it needs to be taken into account when making engineering calculations and assumptions. It is a rare occurrence to encounter a homogeneous reservoir in actual practice. This is because most reservoirs have extremely complex geologies, which can greatly influence the performance of the reservoir. Permeability is one of the most important concepts in reservoir engineering because of the great impact that it can have on hydrocarbon production. Series and parallel flow geometries will lead to different methods of permeability averaging. These different methods of permeability averaging will lead to different values of average permeability, which will yield different values for the flow rate after using Darcy's equation to calculate the flow rate of a reservoir. It is very important to understand and be aware of heterogeneity for reservoir dynamics applications. What is heterogeneity? The reservoir heterogeneity is defined as a variation in reservoir properties as a function of space. These properties may include permeability, porosity, thickness, saturation, faults and fractures, rock facies, and rock characteristics. A homogeneous reservoir is one that does not have variation in reservoir properties. Once again, it is a rare occurrence to actually have a reservoir that is homogeneous. The reservoir property that is of our interest in this presentation is permeability, because we feel it is the most important and fundamental for reservoir dynamics.
Average permeability. In a heterogeneous reservoir, the reservoir contains multiple distinct layers, blocks, or concentric rings of varying permeabilities. Because reservoir heterogeneities such as these always exist, core permeabilities of individual portions of the reservoir must be averaged to accurately represent the flow characteristics of the entire reservoir. The proper way of averaging the permeability data depends on how the various rock layers of different permeabilities were distributed as the rock was deposited. The two different methods for averaging permeability are arithmetic averaging and harmonic averaging. Average permeability. There are two different types of average permeabilities, arithmetic and harmonic. Arithmetic average. This averaging method is used to determine the average permeability of layered parallel beds with different permeabilities. This is the derived equation for arithmetic average permeability. Harmonic average. Harmonic averaging is used when fluid flows through a series combination of beds with different permeabilities. This is the derived equation for harmonic average permeability. Parallel flow. For flow through parallel layers, the pressure drop is equal in each layer. The change in pressure in layer 1 is equal to the change in pressure in layer 2. The total flow rate through the system is equal to the flow rates in each layer added together.
We're going to show parallel flow. We're going to do this by showing how when water poured over this block, it's going to be directed to flow to the colored side more than the white side. The reason for this is because the red side has more permeability due to the more amount of holes we have drilled in it as compared to the white side, it only has one hole. We're going to show how the flow rates for the entire block are going to be additive by showing that when the water is flowing through, the total flow rate is going to equal the flow rate through the red portion of the block plus the flow rate of the white portion of the block.
Now we will demonstrate parallel flow by pouring two equal volumes of water through the system. We should expect the flow rate in the red block to be higher than the flow rate in the white block because the higher permeability in the red block. As you can see, the water is flowing faster through the red block, and it's still flowing through the white block because the permeability in the white block is lower.
Series flow. For series flow, the flow rates in each layer are equal. The total pressure drop across the system is equal to the pressure drop in each layer added together.
Alright, for this part of the project, we're going to show series flow through this block of wood. We're going to illustrate how the top portion of the block, which is not painted, has permeability because we have holes drilled into it. The bottom portion of the block that's painted blue does not have permeability because we have not drilled any holes. To show series flow, we're going to show how when we pour water through the block, there's going to be no flow rate through the entire block. The reason for this is because the flow rates in series flow are the same. So because we have no holes drilled through the bottom portion of the block, there will be no flow rate through the entire block.
Now we will demonstrate series flow through the blocks by pouring water through them. Since the permeability in the blue block is 0, the flow rate in that block is 0. For series flow, the flow rates in each layer are the same. Since the flow rate through the blue block is 0, the flow rate through the entire system is 0. Once poured, we should expect no water to drain through the system. As you can see, no water is draining through the system. Series and parallel flow impact on production. Parallel would be more preferable than series flow because in parallel flow, the flow rates are additive in different layers, and in series flow, the flow rates are the same throughout the layers. In a reservoir with parallel flow, more flow would occur in a layer with higher permeability because it has a lower resistance to flow. On the other hand, if the reservoir had series flow, the fluid cannot choose to flow in the path of least resistance. This will eventually result in lower flow rates for the entire reservoir and thus is not as desirable as parallel flow. Since the flow rates are additive for parallel flow, the total flow rate will be greater than if it were series flow, and the greater the total flow rate, the more production and more profit.
Why is this important in reservoir dynamics? An important job of a reservoir engineer is to be able to accurately determine flow rates for prospective wells. Differentiating between parallel and series flow is important because a reservoir engineer would need optimum knowledge of reservoir fluid flow when estimating hydrocarbon production. Heterogeneity, the varying permeabilities in different locations throughout a reservoir, can greatly affect flow rate, which directly relates to hydrocarbon production from a well. This concludes our presentation on heterogeneity and why it is important to reservoir dynamics. I hope you enjoyed our presentation. Thank you for watching. The following slides will have our works cited, which we